So a vector field, let me completely define it. So a vector field, okay, a vector field, okay. Let's just do it over a plane region R. So over a plane, so a plane region means that we're going to be plugging in x, y inputs. So over a plane region R, okay, over a plane region R is a function. So is a function, okay, that assigns, is a function f. I'm going to call it big F, and I'm going to put a vector symbol over it, okay? You don't have to put the vector symbol over it. I'll assume it's bold. You can do bold or a vector symbol. I won't like -1, forgot the arrow. Don't worry about it. So a vector field over a plane region R is a function f, which is actually a vector, that assigns, and I'm going to give you some examples too, that assigns a vector, so a vector, that vector we're going to call it big F at xy, to each point xy in R. So let me pause here. So I just wanted to write it so you have it in your notes. If you're going into physics or engineering, you'll probably see this again, right? So it's important to go over it a little more thoroughly than the previous section, right? Talk about the definition. I'm going to give you some examples too, some intuitive ones, some that you can actually understand even if you know very little physics. So hopefully that you do. So it takes an ordered pair and spits out a vector. So it's a function that spits out vectors. So when someone says vector field, it's just a function, right? It's just a function. Oftentimes when people say, oh, vector field, you see all these vectors everywhere. They're just drawing a picture. That's the outputs. The outputs are vectors, okay? You see stuff like that all the time. Let's look at some examples. So here's our first example. So given f of x, y, we have a function that is a vector field. That function, capital F of x, y, is defined to be our friend, also known as the gradient of f. So the gradient of f is a vector field, right? So in this case, that would be fx at xy, lots of heavy notation, fy at xy, and then we have the angle brackets. So given a point, xy, you plug it into this function, which is a vector field, and it spits out a vector. If you recall the gradient vector, one easy way to think about it was if I am standing on a rolling hill, right? There's hills this way, there's hills this way. It's just a three-dimensional world, and we're like in the hills. The gradient vector is on the ground, and it's pointing in the direction that tells me to climb as fast as possible. So like, if I'm standing in rolling hills, and the gradient vector is pointing that way, it's a two-dimensional vector on the ground pointing that way, and it's telling me that's the steepest descent. So this is a vector field that points in the direction of maximum increase, right? Of maximum increase. So that's an example of a vector field. Here's another one that you've never seen before. Maybe it's from physics. Maybe some of you have. I took physics, but it's been years. I took physics 1, 2, and 3. Velocity fields. Velocity fields.
If you just add a negative sign, would that show you the greatest decrease?
Yes, it would. And I was thinking that in my mind, and I didn't say it. So that's really interesting. Yes. It's kind of scary. Kind of scary. Right. So if you put a negative, it'll tell you which way to go down as fast as possible. So if you want to sink into the...
Put a negative on which side?
On just the whole thing.
Okay, this is okay.
On the actual gradient. So right, because it points in the opposite direction. So it'll tell you, yeah, it's pretty cool. So here's a picture of a velocity field. So we have a circle like this, okay? And here we have some arrows. So arrow, arrow, arrow. There's a physical interpretation to this, and I'll attempt to explain it the best that I can. So I have some arrows there going that way, okay? And this is this middle piece here. This is called the axle. I guess it's like the middle piece, like in a car. The axle is that thing that goes across that connects the tires, right? Mm-hmm. So the axle is okay. So then here we have little vectors. We have little baby vectors here. I mean, why are they baby vectors? Why are you calling them babies? Because the farther from the axle,
faster you have to be.
The faster you have to be going, the faster it goes, right? The faster. The axle is it's the center. I'm thinking of, yeah, what'd you call it? Axis of rotation. Yeah, I was thinking of a car axle. That's what it says in the book. But yeah, axis of rotation. So you have bigger velocity vectors here, right? Because if you think about it, it's spinning, but it's spinning faster on the outer edges, right? It's kind of cool, right? So these are called velocity vectors. So these are these little, all these vectors that I drew.
I think that would be called the tangential velocity.
Yeah, the tangential velocity. Yep.
T-A-N-G-E-N-I-T-A-M.
Everyone understand why they're bigger here? Because it's something spinning, so you get faster velocity. It's kind of cool, right? Like you get like an intuitive, like a physical thing. I guess that's why it's called physics, right? Because physical, right? Is it? Maybe, right? I don't know, right? So, but kind of a cool example. Let's do another example. This one's even cooler. That one's okay. I like this one. Check this one out. This one has to do with water. Like H2O, the stuff we drink to survive. Soon we'll do a problem. The problems are easy. So here we have the z-axis. Do some 3D stuff. Here we have the x-axis. Here we have the y-axis. And there's tons of these, right? These are just some examples. And then I'm going to draw a circle here like this. Then I'll draw a dome here. And the dome is just, these are some vectors. And then here's a vector here. And then here's a big vector here, and here's a vector here. They're going straight up, and here's a vector here. And you can think of this as water. Okay, it's water moving through a pipe. So it's water. This is also a velocity field. So water moving through a pipe. Yeah, I know. I guess because the endpoints of the vectors are supposed to be here. Right. That his is better. Yeah, his is just better. He's just better. So this is the velocity field.
No, 8 colors.
So can anyone explain why the vectors are bigger here in the middle?
Faster.
Yeah. Does that make sense to you though? Like, so if you have water moving through a pipe, there's no friction, right? The water in the middle of the pipe is moving faster than the waters on the edges of a pipe. Think of a hose, right? Water's flowing through a hose. I guess the water right in the middle of the hose will move at a faster rate than the water near the outer edges of the hose. So kind of interesting, right? Another physical example of...
Droplets.
Huh?
Water going through a pipe, they're like droplets.
Oh, I don't know. I don't know.
Yes, for plants.
That's deep. It's deep. So that's two examples. All right. So that's what a vector field is. We saw three examples. So the gradient vector, a velocity field where you have an axle or an axis of rotation, and then water moving through a pipe. All of those are examples of vector fields. There's many, many more, right? And you will learn many, many more. You will know more than me in a year, right? Because most of you are going into engineering, so you'll do a lot of this stuff, right? We'll take a whole class on fluids, probably. So like your whole semester, this is like a small blip in your semester, perhaps. So what are we doing in this class? We're going to be looking at what's called conservative vector fields. Let's talk about those. So a vector field is conservative. So is conservative, right? Is conservative, and the name has to do with something from physics, the conservation of energy. A vector field is conservative if it is the gradient of some differentiable function. So if it is the gradient of some differentiable function So differential. If you've taken differential equations, this is going to seem really easy, but if you haven't, it's okay. You'll still find it easy, maybe. So you'll see. We'll talk about it. So a vector field is conservative. It has to do with physics. I'll explain it. Maybe you can help me explain it because there's some weird stuff. So a vector field is conservative if it is the gradient of some differentiable function. Let's make it more precise. Let's write it as a math thing. So that is f is conservative. This is the mathematical definition, right? Then we'll talk about the physics. If, do you all remember what the symbol was for exists in this class? The backwards E, yeah, good. If there exists a little f, I once lost a point for writing my E like that on a test because it was crooked. The teacher took a point off. Let me fix it. I am not lying. I was going to say his name, but no, he's a really good teacher. There exists. That guy's a legend. Yeah, he was really the best teacher I ever had. So, is conservative if there exists a function f. What does st mean? Do you remember? Such that. Yes, such that. Let's see. So that means that big F is equal to the gradient of little f. So we'll have to do two things from this section on the test. One, determine if it's conservative. Two, find little f. Little f has a name. Little f is the... I actually have a video of this, by the way, also on the playlist. There's videos for this. So like, there's plenty of videos for this. F is the potential function. So f is called the potential function. F is the potential function.
Just a little f?
Yeah, just a little f for big F.
What's the backward E again?
There exists. There exists. The backwards E is there exists. There exists. There exists. I'll let you write. Then I'll explain what this has to do with physics. Huh? Such that. Such that. Such that. Such that. So, the reason I guess it's called conservative, the idea is, so gravitational fields are conservative, I guess, and electric force fields are conservative. Have you all studied that before in physics? Okay. And the idea is that if you have kinetic, here's the idea, I guess, from physics. If you have kinetic energy, that's the energy of what? Of motion! Yeah, that's what it says in my notes. That's right. Plus, and then you have potential.
Ooh, that's mechanical energy.
Potential energy. That's like, just like, that's the potential it has, right? So, so if you add these up, it's constant. It doesn't change, right? In this vector field. So energy is conserved, right? I guess.
What are we neglecting thermal energy?
Yeah, I guess so. Yeah. What's thermal? It's like heat. Friction.
Or drag.
All right, physics people. Okay. So let me give you the test. There's a test. The test for conservative vector fields, and then we'll just do a bunch of problems, right? We'll do a bunch of questions. So we're only going to do it for the plane. So like x and y, right? We're not going to do functions of like x, y, z. So test for conservative vector fields. For conservative vector fields. Test for conservative vector fields. Test for conservative vector fields. I'm gonna write it a little bit differently than what's in my notes. So here m and n are continuous and have continuous first partial derivatives and have continuous. This is always going to be the case. First partials. I'm not sure if we talked about this in this class. Probably not. I don't remember. There's C1 functions. So did we talk about C1 functions in this class? C1 functions are functions that are continuous and their first partial derivatives are continuous. C2 functions are functions that are continuous and their second partial derivatives are continuous. And then C infinity means that all the partials. We talked about that? Yeah. We did? Oh, it's so good. Oh, it's great. Yeah, it's good. Oh, it's good. Learning stuff. All right, so there's C1 functions. And then F here F is going to be mi hat plus nj hat. You can also think of it as mn in component form. I always think of Patrick when I write component form. So mi hat plus nj hat. That's nj hat. My handwriting is terrible. I'm sorry. I apologize. Nj hat. I just made it worse. Mi hat plus nj hat. Okay, so what's the test? You have to have these things. That's part of the test, but we'll pretend it's not. That's always satisfied. So there's a thing you want to memorize, and in my notes it's written in an uncomfortable way. So here's how you memorize it. So it's del m del, so it's del of the first one, and now the I hat one, you could think of that as the first component, right? Or the x component, right? Because it has an I hat, so it's the other variable, so it's y.
Oh, this is
Yes, it's like the exact DEs. I'm writing it this way so that those of you who are taking DE, it'll make more sense. And then del n, this is like the y component, so this would be the other variable, so del x.
Oh, yeah.
Yeah, you'll probably have one. Yeah, make sure you notice it, right? So,
Gotta check if it's exact or not.
huh? Okay, so we just got to do this, right? I don't know what you're talking about. Let's do a couple problems. All you got to do is check this. If this is true, it's conservative. So on your test, you'll have a couple. It'll say, determine if the vector field is conservative. All you have to do, okay, is work these out. If they're equal, you just say yes. If they're not equal, you just say no. Okay. So you have a 50-50 chance if you guess, but you got to show work, right? So let's do a couple. Oh, the other question you'll have on your test is to find the potential function, right? On those, I'll just say find the potential function. I'm not going to say, oh, if it's conservative. It's just easy to grade. So I'll just tell you to find it, so you don't have to check. All right, so let's do some problems from the homework. Hopefully there's decent ones in the homework. Let's see. Number one's really easy. It's a little bit different. Let's just do it, right? Because we can. It's a classroom. It's December. So we have f of x, y.
It is December.
It is. It's December 2nd today, right? Like,
Right.
I know. Next year we're going to be in 2020.
20.
Hindsight.
Einstein.
Oh, I get it. Okay, so it's x squared. Oh, that's great. X squared plus. And this is an oddball question. It says find the conservative vector field for this potential function by finding its gradient. So all we have to do is find the gradient. So it says find the conservative vector field for this potential function by finding its gradient. So it's none of this. We don't even need, all we have to do is find the gradient. It says to find the gradient. So all we have to do is find the gradient. So let's do it. Boom.
Because that gradient is something.
It's the conservative vector field for, if this is a potential function, then the conservative vector field is the gradient. Or a, yeah. So then all we do here is find the partial with respect to x. So taking the derivative here, what is the derivative of x squared? 2x, very good. You put the 2 in the front, right? You subtract 1. You do 2 minus 1. No, I'm kidding. So it's just 1. No, last day calc 3. No, it's a 1. It's a 1. What's the derivative of this? 0. It's okay. The last day calc 3. Oh! I'm giving you a hard time. Right, that's Fy, right? That's it. That's it. That's it. That's number 1. That's number 1.
Wait, so number 1 is just find the gradient?
Uh-huh.
That's all it says?
That's all it says. You want to do number 2 really quick?
Sure, yeah.
Let's do the same thing.
So let's not do it.
Not do it? Okay, all right. So let's do a harder one. That's the first. Number 4. Great test question. It says conservative. So they give us the vector field. Can someone read it to me?
9y to the 7th.
Uh-huh.
Y I hat plus 8x j hat.
Great test question, okay? Very good question. Why? Because it does require some work before we do it. Like, there's a step you have to do. So, right. So good, Isaac. Yeah. So the first step is to write it in component form, right? So distribute the 9y to the 7th. So this is going to be 9y to the 8th. I'm skipping a step here, writing in component form. Is that okay? Okay, I feel kind of bad. Okay. Okay, all right, see what I did? So you add, right, 7 plus 1 is 8, and then you put a comma. And then 9y to the 7th, so 9 times 8 is 72, right? So it'll be 72.
Let's do y to the 7th times x.
Y to the 7th times x, very good. Okay, so now what we've done is we've rewritten it, okay? So now we have to check. So now we have to check. So,
It's conservative and the gradient should be both on it.
no, we have to check this. We have to check this.
Right, but isn't that, aren't we already doing, if we get the gradient, aren't we already doing?
It's not the gradient, it's just a vector field.
Okay.
So,
So now we got to find big, this is big M. This is big N, okay?
is that parentheses though, before the vector?
Yes, it was. I skipped a step here. So basically what we did was we distributed. So it's 9y to the 8th.
Combined?
I hat, yes, 72, y to the 7th, x, j hat, and then I wrote it that way. Take your time, I'll pause. We got time. We have all the time. So the first one's always m, and the second one's always n. Good question. It's very important. Yes, the I hat part is always the m. Yeah. And then the j hat part is always the n. Okay. Okay. So here's the thing. Here's how you do it. So first you have to do this one. So del m. And then this is the x component, so you have to do del m, no, del y, it's the other one, okay? That's how you memorize it, it's the other one.
I'm and my.
Yeah, that works too. So this is the x component, so it's the other one. So taking this derivative, it's going to be 8 times 9 is 72, y to the 7th, is that right? Good stuff. And then now we have to do this one. So del n, this is the y component. So it'd be what? Del what? Del x. Yeah, this is not bad. This is really easy. You feel like a rock star when you get all these right. Oh, that's just also going to be...
Ooh, so they're exact.
Ah, right. So if you're thinking of...
Exact, then this is a conservative vector.
Yes. So the answer is yes. They're the same. So it's yes. That's it.
Oh, it's genius too?
No.
You couldn't say that?
That's not a differential
Say
equation.
it,
So.
this would be correct.
It's not a differential equation. So you call this m. Okay, so it's del m and it's the other one. So because this is x, you do the y, okay? And then you call this n, and then it's the other one. So because this is y, you do the x. When they're equal, you just say yes. That's it. Does that make sense? Because I know some people aren't in DE, so like, does it make sense? Any questions? Any questions?
Did we do that? I thought we had done that in Calc 3 too.
No. Does it make sense? Any questions? No questions? That's it for this question. The question does not ask for the potential function. Do you all want to find it for practice? No. I think we should.
I think so.
Because on your test you have to find it, right? So let's find it for practice.
Find the potential you say.
On the homework, does it ask you or no?
Is it like potential energy function?
Not for this one. Not for this one.
Is it potential energy function? Is that what it is?
No, I guess, yeah, well, you can call it, yeah, sure. I guess so. I mean, I don't know. I actually don't know. It's just potential function in math. I don't know if they call it potential energy. I actually don't know. So we have this, right? We have this. So all we have to do, oh, wait a minute. Right. So we have to find the potential function. So all we have to do now is integrate each of these, right? Integrate each of these. So you have to integrate this and then integrate this, and then we got it. So you have to integrate this with respect to x, and integrate this with respect to y, I believe, and then set them equal, right?
Get a function of y. If we integrate that, we get arbitrary function.
Yeah, right. So
Exactly like the problem.
I'm going to write it like this. I'm going to write it like this again. So I'm going to write it like it's written over here. So
So we're doing, so we're doing the same thing, except we're going to be doing del m del x, you're saying?
no. We're gonna find the potential function now. So we're gonna integrate each piece. So like we'll integrate this one with respect to x, and then integrate this one with respect to y, and then we'll be done. And we'll set them equal. We have to find little f.
So it's like exact difference.
Yeah, it's like the same thing.
So if it's conservative, it's exact.
You're right. Yeah, if you're thinking of a differential equation, though, right? So we have to integrate this one. So integrate this with respect to x. So that would give us 9y to the 8 x. So we're integrating this with respect to x. So integrate.
We just throw an X on it.
Yeah, integrate with respect to x. I'm going to write that. Integrate.
Is there any like notation for that?
No, I will avoid it just to make it easier. So integrate with respect to x. So integrate this with respect to x. When you integrate with respect to x, you have to add an unknown function of the other variable. So what would the other variable be if we integrate with respect to x? Y. So we get h of y.
Doesn't matter what you call it, right?
No, it doesn't matter what you call it. You can call it anything you want, right? Anything you want. It doesn't actually matter.
And then the other one, you're just going to tack on a y.
The other one you're going to integrate with respect to y. Yes, very good.
Oh, no, but this one actually has y's in it. This one actually has y's in it.
So this one has a y in it. Right, so when you integrate this one, it'll be 72y to the 8th over 8. So what's 72 over 8?
9.
Is that 9? So it's 9y to the 8th. The x hangs out. And we integrate, let me write it. So integrate with respect to y. So we have to add an unknown function of the other variables. So g of x. Let me pause here because I kind of just jumped into this without, like many of you have never seen this before. So when you're finding the potential function, the easiest way to do it is you integrate this one with respect to x, and you integrate this one with respect to y, and you set them equal to each other. Okay, that always works. This is the cheesy way of finding the potential function. So this is a constant, so we attach the x, and then we add an unknown function of y. We integrate this one with respect to y. We add an unknown function of x. And now here's the trick. You read it left to right, okay? And you write, so you can write the answer down. So f of x, y. So you have 9y to the 8th x, right? And that's it, right? That's it. These must be the same. So because these are the same, it must be a constant. So you just add a c. That's it. Right? There's no other variable. This is equal to this, and these must be equal. So if these are equal, it must be a constant, right?
Are they going to not equal each other?
In this class, it's very rare. Most of the time it will. In DE, it's much harder. In this class, most of the time, they're going to be the same, or, I mean, most of the time, in this class, it'll be something like this. In DE, it's much harder. Yes?
What kind of wording would the question be to find that? Or
It'll just say find the potential function.
so it would drop the whole conservative.
Yeah, I want to ask you both parts on the test. It's too confusing. I mean, it's not too confusing. I just want to make it.
It has both in the question.
I know, on some of them.
So,
Yeah, let's do I think number 5. Let's do number 5. I think number 5 might be a good one. So let's do it. 5. That was number. No, that wasn't anything. That was just number 5. So number 5, we have big F of xy equals. Can you read it to me, Jeff? Do you have it?
9y minus x squared I half plus 9x plus y times g.
Thank you. Very good. Thank you. Excellent. Thank you, Jeffrey. So we have this one. I'll go through the whole thing. So this one's a 2-part question. This one asks you, they give you the plus k on all of these. They're really nice. Or plus c. So this one asks you if it's conservative. That's the first part. And then if it is, it asks you to find the potential functions. Let's go ahead and check both parts. Remember, on your exam, I will either ask you to test if it's conservative or...
Be conservative, but potential.
Right. If it's not conservative, there is no potential function. So, yeah.
So if a function is conservative, does that also mean they're exact?
The differential is exact, and if you set it equal to 0, then it becomes an exact differential equation. But that's, yeah. So this is our big M. This is our big N. So we'll check to see if it's conservative, right? So
Del M over del Y.
del Y.
Del N over del X.
Del X. Very good. Very good. So I don't know how you memorize it. I always think of the, unfortunately I know differential equations. Think of this is the X component, so it's the other variable. Think of this as the Y component, so it's the other variable. Okay. So del M del Y is just 9, right? It's just 9. And then del N del X is also 9. So would it be conservative in this case? What do you think? Yes. So you just, so on a test, if it says, is it conservative? That's it, right? You just do that and say yes. It's really easy. Yeah, your last test was ridiculous. I mean, it was like 10 pages or something, that last test?
It was rough.
It was long. It was like, oh my God. In here. There's a lot of topics. Yeah, I was worried. I took it with you all. Remember, I was really worried about the test, so I took it too. I sat over there. I remember. I was like, let's take it together. All right. So now we have to see if we can find the potential function. So I'm going to write it again over here, or we can just do it here. Let's see. So if we integrate this with respect to, what do we integrate this with respect to? X. Very good, because it's the x. So integrate with respect to x, integrate with respect to y. So it'll be 9yx minus x cubed over 3 plus, what should we do? H of y, okay. Equals. And then we integrate this one with respect to what? Y. Very good. So it'll be 9xy plus y squared over 2
Plus g of x.
plus g of x. Sure.
Oh, and then this one, you have to
You have to do.
look at all the different terms and then have it together, right?
Right. So now here's the tricky part. This is the tricky part. So everyone okay with this? So we integrated this with respect to x. So we got 9yx, okay, minus x cubed over 3 plus h of y. This is a really good example because the one on the worksheet is harder, right? These are easier. These are really good questions. And then here, same thing, right? Except it's with respect to y. So 9xy, y squared over 2, unknown function of the other variable. So, any questions?
Yeah. But when on there, we have the 9xy.
So we integrate this with respect to x.
I'm following that. Once we get that though, I can get up to there.
And then here.
What do we do now?
So now you integrate this one with respect to y.
Yeah, I got that too, but I'm saying like,
What do we do next?
Yeah.
Oh, here's the tricky part. Okay, so now you write the answer down. This is the hard part. Okay, so read it left to right. So 9yx. Write down everything you see, okay? Minus x cubed over 3. Okay, plus h of y. So now go to the other side. 9yx, did we already write it down? We did, so you don't write it again. Y squared over 2, did we write it down? No, so we write it down.
we did this in B.
And that's it. Then you just add a c. Let me explain that again. Let me explain that again. So you write that down. You write that down. You're done. You already wrote it down. You don't write it down. You haven't written it down. You write it down. So you write everything down, but only once. If you want to know why, here is why. You can think of this. You can think of this piece here. Okay. Here, I'll explain it like this. You can think of this as del f del x. You can think of this as del f del y. So you can think of this entire left-hand side as f, and this entire right-hand side as f. So basically what you've done is you have f equals f. So this is equal to this must be equal to this, and this must be equal to this. That's what's going on. So it's the same thing. You have f equal to f. So it's exactly the same thing, right? So the easy way to do it is just write it down once, ignore it. You already wrote it down. Write it. So it's just because you want to get all of f. Because both sides are equal to f. Here you have 9yx minus x cubed over 3 plus y squared over 2. Here you have 9xy plus y squared over 2 minus x cubed over 3. You see it? It's both. Let me see it. So 9yx minus x cubed over 3 plus y squared over 2. 9xy plus y squared over 2 minus x cubed over 3. It's just f equals f.
And you don't flip any of the signs.
No, don't flip any of the signs because it's an equation, right? You see it now? Ah, it's good.
That's why the constant is with that.
Yes, yes,
It's all coming together.
yes, yes.
That would actually help.
Yeah, yeah, let's do it.
This is ugly.
Okay. I don't want to do it. It's number 6. Number 6 looks horrible. Let's do it. Number 6. Number 6. I think, well, yeah, I don't know. Let's see. I know number 6 was on the test last semester. I know that for sure. F of xy, big F. I don't know. I don't remember. No, but I changed it. I made it easier. Can someone, it's x. E
The x squared times 4y times the vector 2y I have plus
Okay. And the first step is to figure out if this thing is conservative, right? So first we have to multiply it through, right? So let's do it. We got this. We got skills. So it's going to be 2xy e to the, why do they write it like that? 4x squared y I hat, right? I think I did that right. So 2xy e to the 4x squared y I hat plus x squared e to the 4x squared y j hat, right, j hat. Yuck. Oh, I remember this on a test once. I remember I had a student who got it wrong. I remember her name. I'm not saying it. And she was like, sir, I cannot believe I got it wrong. I'm like, no. That's how she said it. And she was really upset. She got an A. She's like 103 in the class, but she got this one wrong. So now we got to check to see if it's exact, right? We got to check to see if it's exact. Yeah, I remember her face. Okay, so you have to do del m del y. You use the product rule this time, right? No freaking joke. So del m del y. So it's the derivative of the first times the second plus the first times the derivative of the second. So with respect to y, yeah, you got this. I believe in you. Derivative of the first is 2x times the second. So this is e to the 4x squared y plus the first, which is 2xy, times the derivative of this, right? Which is simply e to the 4x squared y times the derivative, right, that's the chain rule, derivative of the inside, right? Because the derivative of y is 1, so you get 4x squared. I don't know, I haven't gotten there yet. I hope not. Let's see. Let's see, so this is going to be 2x e to the 4x squared y, 8x cubed y e to the 4x squared y. So that is del m del y. That's the first piece. That's del m del y. I don't know if there's one that's harder than the test. I know I took last semester's test and changed it because Gabriel was taking it early, and I felt bad for him. So the guy that's not here. Yeah, he took it like the day after our last class, so he missed all of this. Yeah. Plus, I wanted to tone it down. You already had a pretty hard test, so a monster. So let's do del m. So not del m, del n, del what? Del x, good. Del n, del x, very good. Do we have to, we have to use the product rule again, right? Why? Okay, so it's the derivative of the first, it's not that bad. Derivative of the first, we got this, times the second, plus the first, times the derivative of the second, which is just the e.
That's the derivative with respect to x, right?
Yeah.
And you're doing...
Derivative of the first,
Never mind.
times the second, plus the first, doing n, times, what's going to go here? What's the derivative of the inside piece?
8xy.
8xy, very good, 8xy. I hope it's not exact, you know why? Because then we don't have to find the potential function. It is? Oh, sad day. Okay, so it's 2x e to the 4x squared y. No! Let's make it not exact. No, I'm kidding. Let's erase the 2. No, so this will be 8x cubed. That's so weak. 8x cubed y e to, so it's exact. Is it? I'm just saying it is because I'm agreeing with you. No, it's exact. Conservative. So yes, conservative. So let's not think of it that way, right? Because that's something else. That's,
Yeah, but what's the difference?
well, you have equations in that case. But
Like, isn't it like the same?
it's the same technique.
Okay.
You could think of this as a differential. It's definitely called an exact differential. An exact equation, for those of you that are curious, an exact equation is when it looks like this.
So we could solve it on the DE test like this, though, but then in the end, it's like y equals.
Yeah, it's the same. You just integrate each piece.
What it actually
Right.
switch that piece.
Right, you just take everything and set it equal to c. It's a little bit different. So he's saying this, whenever it looks like, whenever it's an equation, it's called an exact differential
Same
equation.
thing you do.
It's
Del m, del y plus
It's the same procedure. Yeah, it's same thing.
We got that 8xy because we did the chain rule.
Yeah, the derivative of this with respect to x is 8xy. So now we have to find the potential function, right? So that means we have to integrate this, and we have to integrate this. and we can do it, right? So let's go ahead and do it, right? Let's do it. So I'll do it here. So first, we have to integrate this one with respect to x, right? And then we have to integrate this one with respect to y. So I'm actually going to show the work this time. I can't just do it in my head. No, 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 no. That day or those days or that particular day is gone. So with respect to, so I'm going to write the integral sign, okay? So like I got to show the work. I mean, I'm not that good. I mean, 2x y e to the 4x squared y. And then this is dx, right, with respect to x.
Is it dx
Or del.
or del x?
No, just dx. We're integrating with respect to x. So we do have to make a u substitution here, right? So we can let u be this piece here. So we'll let u be this piece. So u is equal to 4x squared y. There's only one of these in the homework. Nothing is this hard except this one. And then we multiply, we take the derivative now. So du, it's good for you, it's good.
8x.
8xy
To divide by
dx.
4 on each side to replace that.
Very good. So to make it a 2, right? Because we have to make this look like this.
Is
So
it du or du?
it's du. It's just du. It's just a regular integral. Okay. So divide by 4. Divide by 4. So you get 1/4 du equals 2xy dx.
So
Okay.
you don't have to do some sort of like special, just like show that you're taking a partial integral.
Well, you don't. We did this
But why not?
because there is no notation for it. This just means you're integrating with respect to x. And the context tells us that we're treating y as a constant type. When we integrate, we'll have to add an unknown function of y, right? But okay, so now let's make the substitution. So this is 1/4. 1/4. So 1/4 du is this. Right, so it's just going to give us 1/4 e to the u du. So we're here. 1/4 e to the u du. I'm glad you asked to do this one, Veronica.
Yeah, it's ugly.
Question. So since we're dealing with two functions, we're still saying du though, right?
Yeah. Yeah, it's the same. We did one of these last time at the beginning, right? Just one. And I made a point that you have to add. Remember when I was talking about adding the unknown function? Remember? Yeah. So I know the notation is the same. It's just, so now it'll be, let's just skip some steps. 1/4 e to the u is this. So 4x squared y. Plus, it's not c though, it's a function of what? A function of?
Y.
Of y. So I'll call it h of y. Okay, I'll call it h of
Did you
y.
integrate and plug in at the same time? Did you integrate it and plug in?
Yes, I did. Yes, I did.
Would you mind showing this step, because I...
Yes, absolutely. So you have this,
Yep.
and then the next step is just, and then u was,
Because the derivative of e to the u is e to the u.
yes. I'm going to put this in a box. That's not the answer, but it's important, right? Like, we need it. We're going to have to set it equal to when we integrate this. I'm going to come to this board. I'm running out of room, so I'm going to come over here and integrate that one. So any questions so far on this problem that we've done so far? Yes, Veronica?
Right there, when you took, you did du.
Yes.
Yeah, and you found the derivative. Where'd you get that for? Where'd you?
Isaac. So basically when we're here, you have 8xy and you want it to be 2xy, so you divide by 4. No, good, ask. It's important. That's going to come up on the test for sure. That type of, maybe not this problem, but like, yeah, for sure. I mean, it came up in the last example, I think, kind of. So, any other questions so far? Okay, so now we have to integrate this one with respect to what?
No, y.
Y, with respect to y, right? So to find the potential function, integrate this one with respect to x, integrate this one with respect to y. Okay, so with respect to y, oh, this one's easier. This one's easier, watch. We don't even need to do, watch this. X squared, you don't even need to show the work. Because, I don't know if you remember, but if you,
You can just do 8x.
yeah, because if you have this, you just get e to the 2y over what? If you have this, what do you divide by? 2, right? So normal math, you just do that, right? Whenever you have a constant times a variable, you just divide by the constant. Well, guess what? This is a constant, right? 4x squared is a constant, right? So all we do is we get x squared e to the 4x squared y over 4x squared plus g of x.
No, over 8x.
No.
To get the derivative of the
No, no, no. Think simple. If you have e to the 2y, 2 is a constant, right? You just divide by 2. This is a constant.
Because that y is in front of it.
Yeah, it's a constant. So I know, wow, I was right. I'm really happy that that happened. I didn't think that would happen. I was so ready to make a use of, but you don't have to, right? You can, but you don't have to because it's a constant. It's a constant. So this is 1/4 e to the 4x squared y plus g of x. I'm going to put this in a box because that's important. So this is a constant. So if it was like e to the 4y, you divide by 4, right? I'm looking, oh, look, they're the same. Look, they both have, if those e's are different, something is horribly wrong, right? Like, that's how you know. I'm like, I hope I did it right. Like, I'm like, oh yeah, it's divide. I'm like, I'm gonna look over here to make sure, yeah, we're good, we're good. So now what do you do with these? You set them what? Set them equal to each other, yep. So I'll do it over here. So you have 1/4 e to the 4x squared y plus h of y equals, same thing, 1/4 e to the 4x squared y plus g of x. Oh my God, it's super easy because you just write it down. So the final answer plus c. That was actually easier than I thought tonight was going to be harder. I'd forgotten what I had signed. Yeah.
Is the C a vector?
No,
No, it's not.
it's not. Right, because function f is just a regular function. It spits out a. Yeah, good question. Good. No, good question. Yeah. So as we were doing this, for those of you not in DE, several people were talking about exact differential equations. So what is that? In this case, if you took this vector field and you wrote it like this, I'll squeeze it in down here, and you wrote it like this: 2xy e to the 4x squared y dx plus this x squared e to the 4x squared y dy equals 0. That's an equation. It's called a differential equation. You could divide by dx and you get dy dx. So it's an equation involving a derivative and an unknown function y. And to solve it, you just do the same thing. You integrate this with respect to x, you integrate this with respect to y, and it's very similar. It's very, very similar. It's a little bit different, but it's similar. So it's a little bit different. Yeah?
I know how you got the integral there. What is this, the left, uplift?
This?
Yeah,
This?
where did you get that from?
Oh, I was just explaining that we're just dividing by a number. That's what we're doing here. That's all.
Yeah.
That's all.
Okay.
Yeah. I was explaining how we're doing this, just relating to something simpler. So like if you have a 2, you divide by 2.
I'm like,
No, it's not relevant to, well, it is relevant, but so.
I would have never understood if you hadn't shown that.
Right, because I know, because it's easy to forget that this is a constant, right? Yeah, I know. I didn't notice it either until I wrote it down. I'm like, oh, it's a constant, so yeah. Any questions on this stuff? Anyone like this stuff? Like, it's not so bad, right? It's not bad. It's not bad, right? It's not bad. I don't know if it's going to be this hard in your exam. I really don't know. I don't think so. I can check during the break. I have to delete this part. I have to delete. Got to remember to delete this. Do you want to work on the worksheet? You want to try the worksheet? See if you can do it?
Just start on the
It's
steps.
5 before 7, so that's when we need to delete.
5. Oh no, it doesn't. Oh.
You can figure it out when the class
Yeah. Well, yeah. Yeah. Do you want to do one more, or do you want to try the worksheet? One more? Let's do one more. Let's do the last one on the homework. Number 7. Let's do it. Oh, that one was really hard, wasn't it? That one was pretty tough with the derivative and the product rule. Let's do one more. It's the last one. Number 7. So big F of x, y.
Is equal to 9y over x I half plus 9x squared over y squared j half
9x squared.
over y squared j half.
Do you all want to try it first? Do you want to try this one first? Yeah, try it. Come on, try it. Try to do it. Take your time. Try to do it. It's a good one. I'm going to cheat and look at the answer. So, all right, let's do it. So this is m, and this is n. So here we have to compute del m, del y, right? So 9 over x is a constant. So if we compute del m, del y, so 9 over x is a constant, the derivative of y is 1, so we just get 9 over x. I think I did that right, right?
So,
And then we do del n, del x, right?
18x over y squared.
18x over y squared, yeah, right, because the rest of it's constant. And so is it conservative? Nope, so you just say no.
I think so.
That's it. That's it.
I like this one.
I like this one too.